Alright guys, so today what I want to do is I want to go through a couple of sample problems that use Newton's second law of motion in order to analyze these physical systems that you guys are going to be presented with. Now, as far as these problems go, one of the things that you'll notice is that we will first have to determine what the net force on an object is in order to solve this problem, because both problems I'm going to show you are asking for the acceleration of an object, and what you're going to be given is you're going to be given the forces that act on it. And from Newton's second law of net force equals mass times acceleration, we'll be able to determine the acceleration of that object. So to show you how this works, we have the first problem here with a skydiver. He's falling to the ground. He opens his parachute. The parachute opens up, creates a drag force on him, which will slow him down. You're given, for this first problem, you're given the mass of the skydiver, and you're given the drag force that the parachute produces. So the first thing that you guys want to do when solving these problems is to draw your free body diagram. So I'll just abbreviate that here. Make the dot your skydiver, and there's going to be two forces acting on the skydiver. There's going to be his weight, which I'll symbolize with an F sub W. And then there's the drag force. It's going to be probably larger since it's going to slow them down, so I'll make a little bit larger arrow, and I'll call that F drag. And those are the only two forces that we have acting on them. One of the big challenges with working these problems is identifying correctly rather all the forces that are acting on an object. But for this one, we just have those two forces. So when you go and draw your sketch, it doesn't have to be anything complex. So, there's our skydiver. He's got a parachute on him. Okay. And then draw your forces in here. So we will have a drag force acting up. And I'm going to set my coordinate system to be down is positive. So this drag force will have to be negative 1,027 newtons. I know that his weight also acts down, but I'm not sure what that is yet. I'll explain what you have to do to get that. And then we also know that there's an acceleration due to gravity that exists, g, which is down 9.80 meters per second squared. And the acceleration of the skydiver himself, we don't know what that's going to be. Okay, so we'll just put that as our unknown in this problem. We know his mass, so just list the mass. It's not a vector, but we can list his mass is 93.4 kilograms. Okay, so once again, your sketch, list all the variables that you know, write any vectors into the sketch that you know about, define those, define your coordinate system, and then define your unknown as well. Typical good problem solving technique. Okay, so now we can do the analysis of it, the mathematical analysis of it. Now, the first thing I'm going to need to do here, since my free body diagram includes the weight, I need to know what the magnitude of his weight is. And for weight, the weight of an object, I'll just kind of give you this piece of information. The weight of an object is going to be equal to the mass of the object times the acceleration of gravity at that location. Okay, so which for a lot of our problems is just going to be little g, 9.8. But I want to point out that if you're on Jupiter or Mars or in outer space or whatever, little g will have a different value, and therefore you'd have a different weight. And so although weight is proportional to mass, mass and weight are not the same thing. Weight is a force, whereas mass, is the amount of stuff, the amount of matter that an object contains. So to calculate this weight, I'll say that the weight of the skydiver is his mass times the acceleration due to gravity, which is 93.4 kilograms, times the acceleration due to gravity of 9.80 meters per second squared. So that'll be 915. I'm going to carry some extra sig figs here. Okay, and that's pointing down, so I can make that positive in my coordinate system. And then the next thing that we need to do is to determine what the net force is. So to determine net force, which is what we need to get our acceleration, we say that the net force on any object is the vector sum, and I emphasize vector, the vector sum of all the forces acting on that object. So in this case, it's going to be the weight of the skydiver plus that drag force being applied to him. So plugging those two numbers in, we have his weight being a positive 915 newtons, and then we have that drag force being negative because it's pointing in the negative direction of negative 1027, and we get a net force equal to negative 111.68 newtons. Again, the 0.68, these are extra sig figs, we'll just carry through the end. Okay, so now we have our net force and we're almost there. So we will now use Newton's second law. Okay, so use the second law, which says that the net force on an object is equal to the mass of the object times its acceleration. I made these little vector signs there. The acceleration of an object is always in the same direction as the net force. So after you've added all the forces together, recognize that they're vectors, you get a net force. The acceleration will be in the same direction as that net force. So I can say that the acceleration in this case will be negative 111 over 93.4 kilograms. Remember to use kilograms here. Evil physics teachers sometimes like to give you masses in grams. Don't let that throw you. And the acceleration is negative 1.20 meters per second squared. So we have an acceleration upward of 1.20 meters per second squared, and that would be the acceleration of the skydiver. He will still be traveling down, so I don't want you guys to think in your head that all of a sudden he starts traveling upward. He will still be traveling down, but his velocity will be changing in a negative direction. It's going to be changing in the opposite direction from the way he's traveling. Okay, so that is a fairly straightforward problem involving the use of forces and the use of Newton's second law. Problems in the future could be where we have, where I ask you to find like the distance it travels in a certain amount of time, and I tell you the forces on it, and you determine acceleration, then use your kinematic equations, in order to solve for that. But and we'll do problems like that in class. But I want to show you guys another type of problem involving forces on an object. And in this case, the forces aren't all in like a nice parallel line with each other. Okay, in this case, they're not all horizontal. They're not all vertical. So they're going at angles now. And how do we deal with forces at an angle? Well, take a fairly straightforward example. We have a box. There's two forces acting on this box. One force, force 2, is acting, to the left, but force 1 is acting at an angle of 50 degrees from the horizontal. Okay, as always, we need to make a free body diagram, and we think of all the what are all the forces acting on this box. Shown, I have force 1 acting on that box. I have force 2 acting on the box going to the left. I also have the weight of the box. Okay, so we want to recognize that. And then there's something which I'm going to call the normal force. Okay, normal force, which is the force of the table pushing back up on the box. Okay, so those are really the four forces acting on it. Again, this force is at an angle of 50 degrees below the horizontal. I'm going to use the sketch up here and just add some stuff to it. So I'm going to make to the right positive. I'm going to make, once again, I'm going to make down negative. So I have these two forces acting on it. Then I have my weight acting on it. I have the normal force of the box acting on it. That's my mass. Okay, so I know my mass. I'm asked to find, once again, what the acceleration of that box is going to be. Okay, and I know that my g is pointing down at 9.80 meters per second squared. Okay, I think that's about all that I know for this. Alright, so the question is, for our analysis section, how do we handle that force at an angle? And we're going to handle that angled force very much like we handled the angled velocity in projectile motion. Okay, in other words, what we want to know is what are its components. What is its vertical component? What is its horizontal component? Because you notice in the sketch here in our free body diagram, force 2 is all horizontal. Fn and Fw are vertical. Okay, but F1 has components in both directions, and if we can break it up into components, then we can add, say, that this horizontal component of F1 to F2. We can add the vertical component of F1 to Fn and Fw, and we can get kind of the component of the net force in the horizontal direction, the component of the net force in the vertical direction by doing this. So we're going to break up F1 into components. Okay, so can't spell today. Components. So this is going to be 50 newtons. This angle is 50 degrees. Okay, I'm going to call this F1 horizontal. That'll be equal to the cosine of 50 degrees times 30 newtons. So this will be negative 19.28 newtons. Again, carry some extra sig figs there. I put negative there because, once again, according to our coordinate system, this to the right is being positive. Okay, sorry, made that positive. This should be positive. Okay, so according to our coordinate system, to the right is positive. It's pointing to the right, so it should indeed be positive. And then F1 vertical would be the sine of 50 degrees times 50 newtons, which is our force. Sorry, 30 newtons. 30 newtons is our force. I'll get it right, guys. 30 newtons is our force, so you do that, and you get 22.98 newtons. Okay, and that will also be positive because down is positive. Alright, so now we have a horizontal component for F1 and we have a vertical component for F1. Now, from the problem and from imagining what would happen, you can imagine that the net force in the vertical direction will have to be 0 newtons. Okay, if that net force is not 0 newtons, then the box would have a vertical component to its acceleration on a level table. So it would start to slant up or start to slant down. And we know that that's not going to happen. So we know that the sum of Fw plus Fn plus F1v, all that has to be equal to 0, and it won't contribute at all towards our acceleration. Later on in the course, we'll deal with problems where we can't say that, where we will have a vertical component to our net force, and we can't necessarily say it's 0. But in this case, it is useful, and it does simplify the problem for us. So that leaves the horizontal. Okay, so what do we have going on in the horizontal direction? The net force in the horizontal direction, we know, will be equal to F2 plus this horizontal component of F1. Okay. So what we do is we take F2, which is negative 27 newtons, okay, because F2, remember, is pointing off to the left, which is going to be the negative direction. So negative 27 newtons plus 19.28 carries an extra sig figs newtons, and what we get is a negative 7.7 newtons to the correct number of sig figs. Okay, and that is our net force in the horizontal direction. Because the vertical net force is 0, we can also just simply say that is our net force. So it's negative 7.7 newtons to the left. And then our acceleration will be our net force over the mass of that box, so negative 7.7 newtons divided by 15 kilograms. Okay, and we get negative 0.52 meters per second squared, which would be an acceptable answer. Or you want to just say 0.52 meters per second squared to the left, that is fine as well. Okay, and that is an introduction on how to use Newton's second law and forces in order to solve for an acceleration.